fancy. All right, instruction level parallelism. Talk about this, hazard detection unit, and stalling forward. Okay, so this is the most recent architecture that we looked at in the class. So here we have the forwarding unit. Forwarding unit is helping us with the data hazards that we get at the execution stage. We mentioned that it also helps with the types of hazard that we can get. It's better for me to not call it hazard, it's dependencies, because of the terminology that is used here later. So we take care of the dependencies at the execution stage with the forwarding unit, and also the same forwarding unit can handle some of the dependencies that we get in the memory stage. Okay, talk about the store word case and so on. And then we mentioned that there are some instructions, some sequence instructions like load word that is followed by an R-type instruction, for example. This was an example here, I believe. Yeah, so if we have a load word instruction, and after that we have ALU operation, this we can't fix with just forwarding. We have to stall it as well. So this is an actual hazard. It's not just a dependency. The forwarding unit is going to fix a lot of dependencies, but this is a hazard, and we have to stall the pipeline. So to fix this problem, we mentioned that we place a hazard detection unit in the decoding stage. So this is fetch, this is decoding, right? At the decoding stage, when we decode the instruction, we will find this type of dependency by checking the pipeline's IFID and IDEX. We compare these two pipelines, the RT and RS in these two pipelines, and we find the dependency of the load word. Something that we also added was the IDEX mem-read, because we want to make sure that it's actually a load word, right? Because we do have dependencies when we have a branch here as well, but branch doesn't lead to any hazards. Okay, so we had this condition, and we had the hazard detection unit and the decoding stage of the pipeline who could stall the pipeline. The way it stalled the pipeline was through adding in operations, and the way we did it was through setting all the control signals to 0. In that case, we're not reading anything from the registers or the memory. We're not writing anything to the memory or register, which is pretty much we're not doing anything. If we don't change the state components, these are called state components when you store something in it. State and logic, memory, logic. If we don't change anything in the register and the memory, it's as if we're not doing anything. Even if we do the addition in the ALU, if we don't store it back, it doesn't matter, right? But this is how we stall it. So looking at this architecture, we have a pipeline architecture that supports instruction level parallelism. Like I'm kind of wrapping things up here. Pipelines are these pipeline registers. Instruction level parallelism is when we don't have multiple resources, we don't have multiple ALUs or anything, we don't have multi-threading. We're going to talk about multi-threading at the end of the class, module 9. It's just because we have these registers, pipeline registers, we can execute more than one instructions with the same processor in the same clock cycle. Okay, so in the best case scenario, we want to get an IPC or CPI of equal to 1. So in the best case scenario with the pipeline processor, we want to run one instruction per clock, in considering all the dependencies and everything that we have here. Okay. And then we talked about the forwarding unit, finding dependencies, forwarding the data. That's going to fix some of the dependencies. Hazard detection unit, as I discussed, is going to stall the pipeline whenever needed. And the only case that we actually need this to stall the pipeline so far is the case that we have a load word, and after that we have an ALU operation. Okay. So this is the architecture that we have. We started with a very basic single cycle processor, and now this is where we are. Okay. So let's continue building that architecture and see where we want to go from here. Stalling, forwarding, we already talked about this. So now, all the dependencies that I talked about so far are read after write dependencies, or raw. Okay, read after write. We want to read a register after it is written, and that causes a dependency. Makes sense, right? But there are other types of data hazards that we want to quickly talk about because it's important for the thing that we're going to talk about after this. So one dependency is write after read. So we read the register, we read the register here, just a T0, and the instruction after that we write to it. Okay, so this doesn't really cause any problems, right? This doesn't cause any hazards in the sequence of instructions that we want to execute by itself. Okay, this is the result of the developer's choice to use two same registers for two instructions that are independent. Okay, and it sometimes happens because we have limited number of registers. How many registers do we have for MIPS, integer registers? 32. How many floating point? 32. So if we have a large code, we might have to reuse some of these registers, right? So this is causing a write after read hazard, or antidependence, antidependence, I don't know how to pronounce it. So this is called antidependence. But why do we think this is going to cause any problems for us? Can you guess? If we have an in-order processor, and this is a new term that I'm defining. If we have an in-order processor, which means that it's executing one instruction after the next instruction, then we shouldn't see any problem here. What do you think can be the problem? And you don't have to give me the correct answer. Any answer is fine. We just start the conversation. Sandra, any? Oh, go ahead.
Well,
yeah.
In this kind of case, if you were in something like a loop, you could loop back, and since you put a new value into this register, when it gets to that previous command, it'll have a new value to calculate with it. So that might end up being the problem.
If we have a loop, let me see I correctly understood this. So if we have a loop, we kind of want to go back later.
Yeah.
So let's say we have a loop here as a label. So we want to jump back.
There's no value for T0 because you're now.
So I don't see that as a direct problem, but I see that it can. So going to the loop thing is a good thing, but we're going to talk about it later. But it can. I don't think that is going to cause a direct problem though, because every time we go back, you run add instruction first, and then you add the AND instruction later. But yeah, I mean we're going to the right direction. We're going to see what's the problem. But okay, let me give you the answer, because that's a little bit out of the box, the answer. We had something called reordering, right? So remember that we fixed some of the problems by moving the instructions around, because instead of stalling the processor, you remember that example that we had dependencies, we moved the load board up there and we fixed all the problems. These types of processors are called out-of-order processors. So if you have an out-of-order processor that can choose what instruction to execute first, to get rid of some of the unnecessary stalls and unnecessary dependencies that we have in the system, this is going to be a problem, right? These two instructions are stuck. We always have to run add first and then AND, because if we move AND before this, then we are changing the value of T0. So this add is going to be incorrect. So this should always be, these two are stuck together. That's the problem. If you have an out-of-order processor, AND cannot go before add. Does that make sense? Because if it goes before add, you're changing the T0 value. So this is going to cause a problem if you have an out-of-order processor. Okay? So this is one type of hazard. It's called antidependence, anti-dependence. Another type of hazard that we have is write after write. Okay? So right after write is called output dependence also. And it's the same story. Directly, it doesn't have any problem. Just write the T0. Again, the developer's choice, the same thing. If you have an out-of-order processor, if I move AND before add, this is going to cause issues for the instruction that goes after add. So any instruction that I want to run after this instruction is going to be messed up. It's working with the wrong content, wrong value for T0. So both of these hazards are not going to cause any issues. Dependencies are not going to cause any issues if you have an in-order processor and we don't want to do reordering or scheduling. But the reality is that almost all of the processors that we have, all of the CPUs that we have in market right now, they support out-of-order processing. They do a scheduling, right? It's similar to having a single-cycle processor. We don't really use single-cycle processors, right? We do pipelining, and when we do pipelining, we want to do a scheduling to take advantage of the pipeline that we have, okay? But these kind of dependencies become important if we do reordering or scheduling. Okay, now let's see, let's talk about one of the most important things in the computer architecture course. It's so important that probably in every qualifying exam, you're going to get one question like this. Okay, so they expect us to design an unrolling question in the qualifying exam. Okay, and I design the qualifying exam, and I always do design one question based on this concept. So what is it? What is it? So now I want to see, let's work with a loop. The objective of this example that we have here is to figure out how a compiler unrolls a loop to increase the instruction level parallelism. Right? These are, one of you guys, I think Adam asked a question at the very beginning of the class, and I didn't have an answer at that point. I mean, I knew the answer, but I didn't think of it, was, does it happen at the compiler level or not? These are the optimizations that when you activate the optimization when you're running a code, one of the things it does is loop unrolling. Okay? Sometimes you also define the factor, how much you want to unroll the loop. So these are the things that we're going to learn today. So imagine we have, this should be imagine, not image. Imagine that you have this loop. Okay? It's a very simple loop. And we have x and s values as double precision floating point numbers. Okay? If I will change this to MIPS code, assuming that S1 includes the address in the array with the highest address, and S2 is the address that the last element of the array. So imagine that I have this entire X array and address to the highest element is in S1 and the lowest one is in S2. So it's as simple as, I don't have a marker here. Yeah, it's something like this. S1, S2, these are the addresses. It's stored in these registers. Okay, and this forms the array that I have. So if we have this assumption, and if we assume that F2 has the value of S here, the register F2 has the content of S. So if we convert it to, and the most straightforward code for it is, we load the first element in array X, and we put it in register F0. Because it's the double precision, I'm not sure if you guys remember, but that's just a quick reminder. When we work with double precision floating point numbers, we only use even registers because the odd registers are going to be used automatically after that. So if you use F0, it's double precision, we need 64 bits, you're going to use F0 and F1. Okay, that's why you don't see odd registers here, register indexes. So we load the first array element to F0. Then we add F0, which is this case here, add F0 with F2, because F2 has the value for S, and put the result in another register called F4 or whatever. This is just your choice, F4. And then we store back F4 to memory. Okay? What we do here, we decrement S1 by 8, because it's a double precision number, so it needs 8 bytes. to read the next one. And we create a loop here, we convert S1 and S2, and we just jump back to the loop and read the next element in the array. Okay? You could do it in different ways, you could have an addition here, but that's not the point, right? I'm going to give you if I ask a question, I don't want you to do the conversion, I give you the assembly code, okay? But this is a loop, right? This is how this loop works. We are reading double precision, floating point values, we are adding it with a different number, we store it back. And we do it for 1,000 times in this case, okay? So this is the straightforward conversion of this code segment to assembly code here. Any questions so far? Good. So now if we want to execute this is how we design the question. We give you a table, and this table is giving you the latencies based on the dependencies between the instructions. Okay, let's see how it works. You need to make sense of this table to be able to answer the question. So the instruction that is producing the result is shown in the first column, and then we have the instruction that is using the results in the second column. And then we define some latency values for these instructions. So for example, if I have a floating point ALU operation followed by another floating point ALU operation, and they have a dependency, they need 3 clocks between those instructions. Okay? If I have a floating point ALU operation, and after that I have a store instruction, which is a store double in this case, we need 2 clock cycles between them. If we have a load double, and after that we have a floating point ALU operation, we need 1 clock cycle between them. And if we have a load double followed by a store double, we don't need to stall it. Okay, these are just some, you don't have to memorize this is the information that's provided to you. And this is usually the case because for floating point instructions, we know that it takes longer to finish a floating point instruction compared to an integer instruction. So everything we talked about so far was integer instructions that we could actually forward it, we didn't need to just install the pipeline at all, and that was fine. But the reality is that we have something called floating point coprocessor. Floating point coprocessors, they have their own ALU. So when we talked about the MIPS processor, the ALU that we were showing was integer ALU. Okay, in reality, we have a different ALU, which is for floating point ALU, and that takes longer to finish the task. Now we know we had a marginal floating point, we convert the hardware between integer adder and floating point adder, integer multiplier, floating point multiplier. We know that floating point takes longer. So how much longer? This is a table that is explaining it. If we have a dependency between 2 floating point operations, we have to wait 3 clock cycles. We need to stall the pipeline for 3 clock cycles to make sure that we have the data back. Okay? This usually happens with the floating point cases and not the integer cases. Now, if we don't have any reordering or scheduling, these are the same terms, the loop is going to look like this. If I do the conversion, in the first instruction, I have the first dependency. So this is load F0, and then I want to use F0 for this add instruction. So you do see dependency here. If I look at the table, I have a load, and then I have a floating point ALU operation. So it means that I have to stall the pipeline for 1 clock cycles. So how does it look like? It's going to be this. So we have a load, we have a stall, and then we have the add instruction here. Okay. So now let's look at the next instruction. There's another dependency right here. We'll be adding F4. The result is going to be stored in F4, and then we want to store F4 to the memory. Okay. So this is the other dependency that we have here. And if I look at the table, it's a floating point ALU operation followed by a store double. Okay. The instruction producing the result is add. Instruction using the result is store, as you can see here. So it means that I have to, how many clock cycles do I need here? 2 clock cycles. What it means is I have to add to a stall here, and then I can store it. Okay, and the other 2 instructions are the same instructions, it doesn't matter. Okay, so if I don't have any reordering or scheduling, I have to look at the table and I just find the dependencies. And based on what type of dependency I have, I just add a stall to the pipeline. Does that make sense? So now let's calculate the IPC for this one. Can you tell me what the IPC for this one is? IPC means instructions per clock. So what is the IPC of this one? Andrew, what is the IPC for this?
So there's 5 instructions and 8 clocks, right? So
That's right. So we have 5 instructions, 1, 2, 3, 4, 5, and we have 8 clocks, 1, 2, 3, 4, 5, 6, 7, 8, which means that IPC would be 5 divided by 8, right? This is what IPC is. It's equal to 0.625, right? It's far from the ideal case of 1. The best IPC that we can get with just instruction level parallelism is 1. Okay? You can't go beyond that if you don't have more resources. So okay, so now this is the case here. If we can do scheduling, we might be able to increase the IPC. Any idea how we can improve the IPC on this one with just scheduling? So, do you have any ideas?
Can reorder the
You have
the
it,
code.
okay.
Yeah,
Reorder what?
reorder the code to just like the ADDI to previous one.
So we move the add I instruction, add immediate instruction to here.
Yeah,
That's actually the correct answer, right? So we move the add immediate. It's not going to change anything in the loop. Now the add immediate is moved here, and we are kind of stalling it by running another instruction. That's preordained, right? So add I goes here. There's no dependencies. The loop is going to work fine. And instead of just wasting 1 clock doing nothing, we actually waste 1 clock by actually use that clock by running an instruction. So what is the IPC for this one?
5/7.
5 or 7. 5. So we have 5 instructions, 7 clocks. And it makes an IPC of 0.714. Got a little bit better. We went from 0.625 to this, okay, by just reordering it. But now things are going to get a little bit more complicated. So what would be the maximum IPC if I unroll this loop with a factor of 3? Okay, so let me first explain what unrolling means. So unrolling means I just get the body of the loop and repeat it that many times. So this is a factor of 3. I just repeat the body of the loop 3 times. Okay, and this is how it works. So this is the first part, and it's exactly the same thing again. We load, add, store, load, add, store, with the same dependencies that we had. So we have stalls and everything. Something that you have to pay attention to, one of the things that we change is this offset value. So instead of having add I every time, we could have done that too, but it's just a waste because load already handles the offset. So we just change the offset instead of having add immediate. The offset for this one is -8, means that we are reading the next address, and then we have -16 for the offset, which is the next value. And that means that we have to change this add I to add I -24 because we have a factor of 3, right? So this is a loop that is unrolled with a factor of 3. Repeat the body of the loop 3 times. We change some small things like these offset values and the add I value to -24, and that works. Does this make sense? Okay. It's just pretty straightforward. If I ask you to unroll it with a factor of 4, 3, 2, you can do it. So now, there's another problem here, which is what we talked about. I didn't show everything that we have here, but just look at these registers. So here we have anti-dependence. That's what we talked. That kind of answer that we talked about earlier. So there is an anti-dependence here. How? So we want to load this F0, right? And then we want to use add D here. If I want to do out of order execution, if I want to, let's say, move these instructions around such that I can remove the stalls as much as possible, it's the same thing that we did in the last time, and we just move add I. We can't do it here because of these dependencies. So this is a write after read dependency. Like load D, we write to F0, but here we read it. So if I move load D before this instruction, I'm messing up with the data. Because this add needs to use this load, not this load. Okay? So because of this kind of anti-dependencies that I have here, I can't easily move instructions around. I can't easily reorder the instructions. Okay, so that is causing a problem for me, right? So what do you think can be the problem? How do you think we can solve this problem? There's a very straightforward way to fix it, and that's what compiler actually does. How can we fix anti-dependence? Just think out of the box a little bit. Like it's not something that we talked about before. Mason, any ideas?
Store a value to another
Well,
register.
We have a lot of floating point registers at our disposal we could use as other registers.
Perfect. Yeah, that's the right answer. So why are we shy? Just give the answer. That was fine. Yeah, so we have a lot of floating point registers, right? So why do we use F0 again? We can do something that is called register renaming, right? It's called register renaming. That's the concept. Register renaming just changes the name of the net registers. If you have some extra registers, in some compilers, they actually use dummy registers too, right? They have they only may use, for example, F6, F8. They have some extra registers kept for register renaming, right? But here, we just stick with the registers that we already have. So there's nothing with the code that's going to change if I change this F0 to F6, if I change this F4 to F8, right? And the same story after this point. We have F10, F12. It's the same exact code. We're just introducing more registers to the loop. Doing this by register renaming, we are removing all the anti-dependencies. Okay? So now we can move things around and play with this and improve the IPC. We can do scheduling, reordering, improve the IPC. Okay? So let's go to the next slide. So this is after everything is changed. Now we want to do scheduling. Okay? So help me with the scheduling. Let's do it together and see how we can get the maximum IPC here. So any ideas? Raise your hand if you have any ideas about moving things around. How can we do it? And we want to get rid of this install somehow. So we want to add some instruction between load and add. Go ahead, Blake.
Well, I guess if you've changed all the registers to have different, so they're not all the same, can't you just do a bunch of loads in the beginning?
That's an idea, right? We do all the loads. Let's say we do all the loads from the beginning. Okay, 3 loads here. Then we do, what do we do next?
Or at least fill them into the stalls.
Yeah, so you want to move one load here, another one here? Yeah, but there is a better way of doing it. Go.
If you do like all the loads, then next to all the adds, then next to all the store.
For whom? Yeah, that's the right answer. Yeah, so we do all the loads first. Let's see how it changes. We do all the loads first, and then we do all the adds, and then we go all the stores. So now the first thing that we were worried about is every add that comes after a load, we need one clock cycle between them. So look at adds and loads. So all of them have more than one clock cycle within them, right? So we have load. The next one that we use F0 is here. So we have 2 clock cycles between these 2 instructions. The problem is fixed. Okay? We have even more than 1 clock cycles between them. Then the next concern was 2 clock cycles between add and store. So by adding these two add instructions here, so we have add, and the results going to be stored in F4 here, then we want to store back F4 to the memory. Because we have these two add instructions, we have enough delays between two instructions. Same is true with this add and this store, and the third add and the third is store. And then we have add up. What is the IPC here? Don't even have to do the calculation, but if you do, it's 11 instructions, 11 clocks, IPC of 1. That's the best case scenario for an out of order processor. Now, if I add a loop unrolling a factor 4, the only thing that I'm really saving at that point is less add I and branches. Right?
Okay. So this worked out because we had a factor of 3, and it wouldn't work out with a factor of 3 and above.
It would, yeah, that's what I'm saying.
But if we had a factor of 2, then that would cause problems
Yes.
because we don't have enough instructions to
Yes.
fill.
Yes. If it was a factor of 2, then we wouldn't have enough. That was a really good point. So if we have a factor of 2, we wouldn't have enough instructions. We would still need some stalls. And that means that we couldn't get IPC of 1. But if we have factor of 4, because something I want to say here as well, which I didn't pay attention at the time, is that you have to look at the loop counter. Okay, I didn't use a factor of 4 here just because it was just too much copy and pasting in the slides. I don't want to mess it up. But the reality is that we can't really do factor of 3 because our loop has, if you go back here, the iteration is 1,000, right? So it should be divisible. We have to have some kind of, so 1,000 you can divide it by 3. So you can do 2, 4, 8, right? So that's something you need to pay attention. But for this concept, I didn't really care about it. I can just change it to something that's divisible by 3, and it works, right? Actually, if you go to the book, and this is not in the computer organization book, it's actually in the quantitative analysis book, so I'm using multiple books here. But there's an example there, and that example uses a factor of 4, right? The reason they use factor of 4 is because it's divisible by 4. 1,000, go ahead.
So with the unrolling, you can't do 3 because 1,000 is not divisible by 3. But couldn't you use 3 and then at the end do 1 extra?
Absolutely, yes.
So then it's 999 and then 1 at the end.
Absolutely. Then you have to, but that's beyond loop unrolling, right? That's just doing loop unrolling. I'm not sure compiler is smart enough. I mean, they can do it.
So it'd be easier to just use 4 since you don't have to worry about the extra step at the end.
And also, if you do 4, I get to you, Sander. If you do 4, you're gonna save a little bit of add I amp branch equals 2, right? So that's what I'm saying. After this point, you're not gonna change the IPC that much. But if I do, for example, a factor, let's say there's 1,000. We have 1,000 iterations. If you do a factor of 4, you repeat this loop 250 times. Okay. Now, if I do, so it means that you have to multiply this, you execute this add I and branch not equal for 250 times. Now, if I do a factor of 8, the IPC of the loop doesn't change that much, but I just need to execute this add I and branch not equal for 125 times. So after some points, the more unrolling you do, it's not going to change the IPC of that loop that much, but you're going to execute less add immediates and branches, which can be a big deal because branches are actually energy consuming. Then they're going.
So, how big of a factor could you do? Like, if it ran out of registers, would it just say to just cut it there, or would it reuse the older registers and know that it could do that safely?
So that's why they usually use. That's when I said that they have some dummy register just for this. Is the usual thing to do is not reusing the registers that you have for in the main code. So later when we talk about multi-threading, I have another example that does unrolling, and then we distribute it in multiple threads. Then you can see that we actually have registers called R that are just used for that. And if we don't have enough of them, it just doesn't do that much unrolling. So now the fun part. So your second project, and by the way, I asked the TA to grade the first project by the end of the week. Your second project is gonna be changing your code to floating point now. Okay, so you had an integer working. So you have to make the same code working for floating point. Then we're gonna have longer vectors, okay? And then you do loop unrolling. So you unroll the loops, and then you provide an analysis for me that says, okay, what's gonna happen if you unroll the loop for the factor of 2, 3, 4. Then you see the differences when you do unrolling, okay? So your second project is gonna be about that, changing things that what you had to floating point vector multiplication, and do unrolling with different factors. We're going to provide more details later, but you can be ready for that. If you want to start the project from now, the least you can do is just change it to floating point for now. And then I will give you a table, because unfortunately I don't think Mars can have the option of adding latencies between the instructions, so it's just going to execute everything as if it doesn't get the dependencies. Or maybe it does. We have to do a little bit of research more. I've never tried using it for that. But we're gonna ask you to do some analysis yourself. So assuming that we have this kind of delays, you just need to calculate the IPC and so on for your code. So you can start with changing it to floating point. And it's a fair assumption to say that your numbers, the numbers that we're going to test with, are small numbers. So they're going to be stored in one register. You don't have to deal with two registers at the same time. Same story that we had for high and low. It's the same story here. The floating point numbers are going to be small enough, and you just need to read one register for that. Okay, so this is what loop unrolling is. This is how we get an IPC of 1 for this case. All right, any questions? This is a very important topic. As I said, every qualifying exam, every comprehensive exam, you try to have something about unrolling. In your midterm exam, I'm probably going to give you one of the qualifying exam questions from previous years, so you get some idea about it. All right, so now let's talk about another type of hazard, which is control hazards. Okay, control hazards happen when we have a branch, and we have to make a decision what instruction we should execute after the branch instruction. Branch, if you remember, we calculate the branch target address. The way that branch works, if the condition is met, we go to another place in the instruction memory. Like this is the case, for example, here. If these two are equal, then we want to jump to this instruction. For all of you guys haven't seen this type of branch instruction before, because we have labels usually. But one way of having branch is literally putting a number here, and then what you need to do, you have to add this number with PC plus 4. So the PC is 40 here, PC plus 4 is 44. If you add 44 with 28, you go to address 72. Okay? This is me describing what this figure is showing. So you have two options. You either fetch the next instruction when the branch is not met. Okay, branch condition is not met. In this case, if 1 is not equal to 3, or if they are equal to, if register 1 and register 3 are equal, then you want to jump to branch target address, which is the PC equal to 72. Right? So this is causing some problems for me because I don't know what the next instruction that I want to fetch should be. In the pipeline, you want to keep fetching instruction one after each another. Okay? So this branch is a control hazard case that I just have to wait and see what instruction I should fetch next. Okay? So when do I know about the decision of the branch? It's at the memory stage. Why memory stage? Let's go to slide 24, just a reminder, because I don't want to get confused. Slide 24 is here. So if you look at this is where the branch decision is made. We use the ALU to do the subtraction, we get the result of the 0, then we go to the memory stage. At the memory stage we have this AND gate, and then we decide what the next instruction should be. Should we use PC plus 4, or we should use the branch target address, right? So at the memory stage we make a decision about the next instruction. Now let's go back where we were, which is here. Okay, so if we know where we should go at the memory stage, this means that this is where we figure out the next PC. But when we are here, we have already fetched 3 instructions, right? We have already fetched AND, OR, and ADD because that's how the pipeline works. So what it means is that I have to go back somehow, find a way to go back, flush the pipeline, very expensive process, okay? So how can I fix this problem? The easiest way is that when I'm at the decoding stage, at this stage, when I decode a branch, I just install it for 3 clock cycles. Every time that I decode a branch, when I look at the opcode and I find out this is the branch, I just stop, just install everything for 3 clock cycles. And we know how to install the pipeline, we just send control signal 0 to the pipeline. Right? That's one solution. But it's very expensive. Like, we don't want to do this. 3 clock cycles is way too much. Imagine that we have a loop, and that loop we're going to call the branch thousands of times, and every time we want to install it for 3 clock cycles, it's just awful. Right? It's one of the things that we don't want to do. Okay? So what should we do? So branch prediction. What's the idea behind branch prediction? It's a simple method based on which we just predict something without any information, right? We just say, okay, let's say we take the branch. And we move forward as if the branch should be taken. We don't know if we should take the branch or not, right? So just to make sure that you know, when I say take the branch, it means that condition is met, I have to jump to another broken counter. So let's say we take the branch every time, okay? And then we move forward, and if it was a wrong decision, we just pay the cost, right? We're hoping that we find a mechanism through which we can improve the IPC, and that only works if we have more correct prediction than incorrect ones. Because the cost of going back is more expensive than cost of installing. Sometimes. It could be. Okay? So branch prediction is that. Make a prediction, stick with that. 3 clocks later, you know whether you made the right decision or wrong. If it was a correct decision, you're good. If it wasn't, then you have to go back and flush everything, flush the pipeline, redo everything again. Okay? They're hoping to find a mechanism that's a little bit smart. Okay? So we have a static approaches for branch prediction. Okay? Static approaches is something like this. Always predict the branches will be untaken. Always predict that this will be taken. It's a static approach. We can make it a little bit more, it sounds like intelligent. We can say always predict the branches at the bottom of the loops will be taken, and predict the branches at the top of the loop will be untaken. That's right. Yeah, I thought I have a typo here. But the branches at the top of the loop will not be taken. The branches at the bottom of the loop will be taken. So that's how we created the loop, right? We had 2 ways of creating a loop. We had the branch in the beginning, let's say BQ, and then we had the body of the loop, and then we jumped back, right? So if branch is at the top of the loop, probably we take it, it's going to be taken less times. Probably we're going to run this loop. The condition is not met. We run the loop, we jump back. So we do this 999 times, and the 1000th time, we're wrong. That's kind of smart, right? You know, just always predict that it's not going to be taken. How do you check that? Just a little bit again, one of those questions that can be out of the box. How do you check if the branch is in the top of the loop or the bottom of the loop? Go back to instruction and coding.
Code's a negative or a positive.
Oh, perfect, yeah. So that's an I-type instruction, and we had an offset field, right? So if this offset field is positive, it means that's at the top of the loop, because we're going to go to instructions here. If it's negative, it means that's the bottom of the loop. So you check the sign of the offset field after seeing the opcode, and you decide whether you want to take the branch or don't want to take the branch. And that decision can be made at the decoding stage, right? When you decode it, right there you can say, okay, take the branch, not take the branch, based on the sign of the offset of the branch. Okay, so you basically check just one bit here. If this one bit is 1, it's a positive number. If it's a negative number, if it's 0, it's positive, and then you take the branch based on that. Okay. Another way of creating a loop was putting this branch at the end, and that means every time you're taking the branch, and one of the predictions is going to be wrong. So we are good 99% of the time, and 1% we make a mistake. Okay. So that's actually smart. No, that's but still static. It's the same exact thing over and over. So the guy who the invention was a dynamic branch prediction. Okay, so dynamic branch prediction, we keep a history of the branches, and we make a decision based on that history. Okay. So how does that work? Before showing how the dynamic branch prediction works, I want to show you the cost of the mistake that we make. So if we make an incorrect prediction, we should do two things. One is we have to create no operations, which means stalling it. If the prediction is wrong, we have to stall everything. But it's not stalling is not enough. We have to flush the pipeline too, because we have already let 3 instructions in. Few instructions in. So everything is wrong, so we have to go back. That's why I say it's more expensive than just stalling it. So if you make an incorrect prediction, it's worse than just stalling the pipeline. But to reduce that cost, there is something that we do, which is we bring the evaluation a step a little bit earlier. Okay, so the way that we evaluate branches is that we wait until the execution stage, and we use ALU to do some kind of subtraction, and then at the memory stage we find out whether it was a correct prediction or an incorrect prediction, right? This is how it works in the basic system, basic architecture. But there are ways that we can improve it. One thing we can do is that we can add extra hardware to the decoding stage. Okay, so we move this branch evaluation stage to the decoding, and right there we evaluate the branch. So in this case, if we have a problem, we don't have to flush the entire pipeline. We're just wrong for 1 clock cycles. Okay, so the branch decision can go to the decoding stage, and also we have to calculate the branch target address earlier too. If you remember, we calculated the branch target in the execution stage as well. We had an extra add on top of the ALU that we had, which was working with the immediate number. Maybe it's better for me to show it, so you just don't imagine everything. So this one doesn't have it. Let's go back to, you know what? Actually, I think I was smart enough to include it in the slide after that. So let's see. Yeah, okay. So this is the data path that we had. This is actually the slide after this slide, so I didn't have to go back. So if you look at this doesn't have these modifications that we talked about. The branch target is calculated here at the execution stage. So the immediate comes here, we shift left, we added the PC plus 4, and so on, right? This is done here. If we want to reduce the cost of the branches, now what is the cost of the branch? Flushing the pipeline, or stalling the pipeline, that's the cost of the branch. If we want to reduce the cost of the branch, we can move this to the decoding stage. So we kind of calculate the branch target address in the decoding stage. And we also move this entire AND gate and finding whether we should do the branch or not through using the ALU to this stage 2. So we have to add extra hardware to the decoding stage to evaluate the branch a little bit earlier. Okay? So how do we do it? This is the hardware that we add to it. When we decode the registers, we just add a simple comparator here to just check if they're equal or not. So we don't use ALU for that anymore. So right here we evaluate two registers. We look at the opcode. If it's a branch, so opcode, we already have the opcode here because we're decoding the instruction. So if it's a branch, and if these two guys are equal, let's say if it's a branch equal, and they're equal already, so right there you know that not only you have to take the branch, but also whether your prediction was right or wrong. So you calculate the branch target address, you evaluate your prediction. Here we are also still making a prediction, right? We can't get rid of making a prediction. That we should have in mind, because when you are evaluating the branch instruction, your next instruction is already fetched, no matter what. So the earliest you can make a prediction is at the decoding stage, where you see the branch for the first time. It's okay, this is a branch. But when you are evaluating your branch there, you have already fetched the next instruction based on the branch prediction unit. Okay, so basically we can say that the branch prediction is somewhere here. So every time you want to fetch an instruction, so that's the thing that branch prediction unit does. Every time that you want to fetch an instruction, the branch prediction unit in the fetch stage is gonna tell you whether you fetch the instruction after PC plus 4 or the branch target address. You already make a prediction. So when you're here, this is where you evaluate whether your prediction was right or wrong at decoding stage. But the fact that we moved it from memory stage to decoding stage, it means that we only need to flush one pipeline. We don't have to flush all the pipeline registers because we did the evaluation at the memory stage. So here, the hardware that we add is a comparator here, but also if you look at this, we're moving this entire block that does the branch target address calculation to here as well. So the branch target is also calculated at the decoding stage. This reduces the cost of an incorrect prediction to one clock cycle stall and one pipeline flush. Okay, now let's see with one example how it works. So this is an example that we have. We have a branch equal at the second instruction. Before that we have subtraction. After that we have AND. If the branch is actual equal, so if it's equal, we multiply, we jump to address 72. Okay? So, but here we have to make a prediction. Anyways, so now let's see. At clock 3, we have the subtraction in the execution stage. Subtraction is the first instruction, right? It's already in the execution stage. Branch is in the decoding stage, and AND is already fetched. Okay, so here we're assuming that our prediction is that the branch is not taken. So at this stage, at clock 3, when we want to fetch the next instruction, the branch prediction unit has told me that, okay, go ahead with fetching the next instruction, because our assumption is the branch prediction, branch predictors. They're saying our assumption is that the branch should not be taken, so fetch the next instruction. And the next instruction that it fetches AND. But in this case, let's say that it was a wrong prediction. We want to see what's going to happen in the pipeline. Let's say the branch predictor said that, okay, take the next instruction, but when we get to the clock to this part, by comparing the registers, we notice that, oh, that was a wrong prediction. So now what should we do next clock? In next clock, what you do is you immediately change this to a bubble and no operation by setting the control signals to 0. What it means is that in the next clock, your branch is going to the next instruction, but this, when it gets to the decoding, instead of setting the control signals for add, we just stall everything. So this means that this incorrect prediction is not even sent to the pipeline. Because this is where we set the control signals based on the instruction at the decoding stage. So if I can predict it earlier, and when I get to this point in clock 4, I just ignore add. Okay? But at the same time, you have to be careful enough that the next instruction that you want to fetch is the branch target address. Okay? So and that's why we do the branch target address calculation here. Because then we already know at this stage, not only we know that we made an incorrect prediction, but also we calculate the branch target address for the next instruction. So the next instruction that we fetch is going to be the correct instruction. Right? So just for you to know, the branch prediction unit is here. And then we make a decision based on the branch prediction result. And then we stick with that and we pay the cost if we make a mistake. Okay? Clock 4, operation, and we're good. Okay, so what I just mentioned here is having a branch prediction unit that corrects itself immediately, but that comes with the cost. And the cost is if you don't add, so this guy doesn't have a history, right? So it can get stuck at keep making incorrect predictions and keep correcting itself, right? So it makes an incorrect prediction, immediately corrects it next clock cycle, then again makes another incorrect prediction, immediately corrects itself, and that can cause a problem. It might not be that intuitive, and that's why it makes the next thing I want to talk about the invention, right? It doesn't sound intuitive because you think, okay, what is wrong with correcting yourself, right? You just correct it every cycle, you fetch it next time, and probably in the long run, it should work fine. Okay. Now, let's see an example. So this is the next thing I want to talk about, and the last thing that I want to talk about in this module, and the module is done. This is the end of module, the last 2 slides of module 7. So this is a 2-bit dynamic branch prediction scheme. Okay. It uses a state machine which has 4 states: 0, 0, 0, 1, 1, 0, and 1, 1. Okay. So every time that you want to make a prediction, you are at one of these states. If you're at state 0, 0, your prediction is take the branch. If your state is 0, 1, your prediction is take the branch. If you're at 1, 0 or 1, 1, you predict that you don't want to take the branch. Okay, so that's how states work. But how do we go from one state to another state? If we are at the state 0, 0, and we predict, at this stage we predict that the branch should be taken. We go to the decoding stage and we notice that that was an incorrect prediction. But we don't change our mind immediately, right? We go to the state 0, 1. In the state 0, 1, our next prediction will still be take the branch, right? We don't change our mind immediately. We just doubt the decision, but we still make the decision of taking the branch. Okay. Now, the second time, we take the branch, but again we notice that that's an incorrect decision. That's when we change our mind. That's when we go to state 1, 0, and at state 1, 0, for the next branch, this time you don't take the branch. So it takes, if you're at state 0, 0, you have to make 2 consecutive mistakes in order to change your mind from taking a branch to not taking a branch. Okay, you're kind of adding a delay. You're just not jumping around, right? The same story with not taken. So when you're at the not taken, when you predict not taken, and your prediction is not correct, which means that the prediction, this blue line that you see here, is the actual loop evaluation. This is what it had to happen, but our prediction was not taken. Then we noticed that we were wrong. We had to take the branch. We go from state 1, 1 to state 1, 0. At state 1, 0, we still make the decision that the branch should not be taken. If we are incorrect again, it means that the branch should have been taken. We go to the next state. So if you look at the arrows here, these guys are showing the actual branch behavior. Inside this oval, we can see what we actually do. Okay, so let's do this example. We have a loop that branches 7 times in a row, and then it doesn't take the branch once. Let's say there's a loop behavior, the iteration of the loop is whatever, 8 or whatever. So it takes the branch 7 times, and then it doesn't take the branch once. So what is the prediction accuracy if you use the above 2-bit prediction scheme with the initial state of 0, 0? So we're at here. We want to see what would be the branch prediction accuracy. So when we're at state 0, 0, so what you see up here is the actual behavior of the loop branch. This is how it should work. Ideally, if you make all the correct predictions, it should work like this: taken, 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 and one taken at the end. Okay? So if you're at state 0, 0, our prediction would be take the branch. And when we go to the decoding stage and we evaluate it, we see that we actually made the correct decision. So this is true. And that means that because we made the correct decision, the branch was actually taken, we remain at state 0, 0. Okay? We don't change anything. So the next state would be 0, 0. Again, the prediction is taken, and the branch should be taken. That's again correct. Same story. We go all the way to this stage. So everything is true until the very last stage. In this stage, our prediction would be take the branch, right? But we actually should not take the branch. So this is the false prediction. So what would be the next state if we had more steps? Can you tell me what would be the next state? Sam, go ahead.
Would it be 0, 1?
It would be 0, 1, right? Because we're at 0, 0, we made a mistake, now the state is going to change to 0, 1. What is the accuracy here? 7 divided by 8, 87.5%. Let's solve this question. This is another example. Same story. Take 7 branches, you don't take it at the very last time. The initial state is 1, 0. Okay? So you help me with this. I'm going to state 1, 0. What is the prediction?
We're not taking the branch.
Prediction is we're not taking it. The actual branch behavior is that we should take it. So this is a false prediction. What is the next state?
0, 1, 0.
0, 1. Okay? So 0, 1, the prediction is take the branch. It's the correct prediction. What would be the next state?
0, 0, 0.
0, 0. Take the branch. And we are stuck at making correct prediction until the very last step. The very last step, prediction is take the branch. You already know this. The correct one is we shouldn't take the branch, so it's a false prediction. The accuracy would be 6 divided by 8 is 75%. Simple scheme like this is actually implemented in a lot of processes that we have these days.